Reliability, Chapter 11. In this chapter, we are going to understand the concept of reliability, also the reliability functions and the failure rate, reliability models and component relationship, and the fields of maintainability and availability. So let's start defining reliability. And a simple definition is quality over the long run. Reliability is the ability of the product or service to perform its intended function over a period of time. So reliability will help us to answer the question how to prolong, predict, and guarantee product life. It is formally defined as the probability that a product or piece of equipment or system performs its intended function for a stated period of time under specified operating conditions. So if you notice those highlighted words, probability, so will be a percentage or a number between 0 and 1. Performs has to do with the ability to function. Time, this is very key in reliability because it's very similar to the quality definition, but it has to do with the time. And it will be under those specified operating conditions. So you have to take into consideration those different operating conditions because that will give you more information about how long the product will last. So the basic objective of reliability is to meet the product's operational goals. And a product that works for a long period of time is a reliable one. And you're going to hear this a lot. And since all uniform product will fail at different times, reliability is a probability. When you have a system is composed by different components. And every of those components have a reliability value. It means we know, or we should know, when each individual component will fail. And that information is key to understand how long our product as a complete product will fail. Now there are 4 elements associated with reliability: chance or likelihood or numerical value, and this is the part of the probability. It indicates that the product will function satisfactorily during a particular time. You also have the intended function or performance, and we know the products are designed for a particular applications and they're expected to be able to perform those applications. The third factor, the expected or desired operating time or life. This is, in other words, how long the product is expected to last. And the fourth one is the operating or environmental conditions. You need to take into consideration if a product that is designed to function indoors would not be the same or would not last the same if you are going to be using this product for outdoors. There will be exposed to sun, to the wind, to precipitation. So those different environmental conditions must be part of your reliability study. Part of your second factor, the intended function or the adequate performance, it has to do also with meeting the standard. And we know that a standard is needed. And a standard must define what is meant by adequate and must contain effective measurement criteria for comparing actual performance to the standard. The standards also must include variation. We know that we have variation, so the total variation from high to low is known as the tolerance. So from a standard, we're going to come up with a tolerance, and those are the ones that our product must meet. Now, good standards are written, and written standards are known as specifications. So from a standard, you have the different total variation, which is the total, and also good standards are known as specifications. In reliability, we have 2 types of systems, or actually 3 types. The first type is the series system. The second types are the parallel system. And the third time is a combination of both, series and parallel. So let's start understanding the series systems. And for series systems, the reliability is the product of the individual components. And this is what we call the product rule. In a series system, you will see the components are arranged this way. And to calculate the reliability of the complete system, you have just to multiply the individual reliability for each component. When you see series system, and maybe if you have taken electronic, you will see this, If one component fails in a series system, the whole system will fail. Also, as components are added to the series, the system reliability will decrease because it's a product rule. So what you have to make sure that if you have to add more components, the reliability of those components must be very high to justify that the system reliability will decrease. Also, if all the components within the system has the same reliability value, you can use this formula for a reliability system, which is the reliability value of each component times the number of components. And this is how we calculate the equivalent component reliability. If you want to find the unreliability, remember, because it's a probability value, you just have to subtract that probability of the system from 1, and that will give you the unreliability of the system. That is for components when the components reliabilities are equal, and if they're not equal, you just have to subtract the multiplication of them from 1. That is when you have the reliability of each component value. So this is a variable that you will know. Also, reliability can be calculated knowing the failure rate, and this is this symbol lambda. And if you have the failure rate information, the reliability of the systems is e to the power of minus t, which is a total time, times the sum of the failure rates for the components. And that will give you the series system reliability using failure rate. So this is an example. It says a system consists of 100 components and they're connected functionally in series. Each component has 100 reliability hours of 0.99. So we need to calculate the reliability of the system. So what do you know here? You know that we have 100 components, so that's our n. We also know that each component has a reliability of 0.99, and that's the individual reliability. So because all components have the same reliability, we can use the formula that is the reliability of the component to the power of the number of components, which is n. So in this case, it's 0.99 to the power of 100, and that will give you a reliability of 0.36 or 36%. You see, even though the reliability of the components is very high, 99%, because you have 100 components, the reliability of the system will be very low. Okay, this is in case that we have series systems. The other type of systems are parallel. And a parallel system is defined as a complex set of interrelated components, and they are connected in such a way that a redundant or standby part can take over the function of a failed part to save the system. When we talk about parallel systems, and once again, if you have taken electronics, you will see this. If one component failed, your system can still work. The only way for the system to fail is that all the components will fail. So in a parallel systems, you will see that the components are arranged in a different way. And to calculate the reliability of the system is 1 minus the multiplication of the unreliability for each component. And unreliability will be 1 minus the reliability of that component. So that's how you calculate the reliability of a parallel system. As I mentioned before, when a component does not function, the product continues to function using another component until all parallel components do not function. This is the only way that a parallel system will stop. In the case of a parallel system reliability, it will be the value of the system will be higher than the value of those individual components' reliability. The parallel reliability will increase as the number of components increases, and because this is the way that we calculate it. Marginal probability refers to the increase in reliability as components are added. A redundancy increases in parallel system, and it is important to balance the cost involved. And this is because you will see that there are a lot of designs that will have a lot of redundancy or redundant systems, and it's to make sure that if one fails, the other one can take place and the system will continue to work. But you also have to make sure that you balance the cost that involves to include redundant components. In series system, remember that the cost of adding another component must never be greater than the benefit received from the increased reliability. And actually this will apply to both. The third type of system we have is the combination of series and parallel. The way that we determine the reliability is by computing the reliability separately, and you use the rule that applies to either series or parallel system level by level until the entire system is completed. For example, you could work the parallel pieces first, and then the whole system will be in series. Then you calculate the systems using the series formula. That could be an example. Let's look at this example. We have a combination of system because we have series components and there is a parallel component here. So the way that you should do it is you first work the parallel area, and the way that you work parallel system is 1 minus the multiplication of the unreliability for each component, and then the whole system now is in a series, and you calculate the series, which is the multiplication of each individual reliability. In this type of systems, as the number of components in series system is increased, the system reliability decreases at an increasing rate. For any series system with more than 20 parts, the part reliability must be greater than 95% for the system to have much usefulness. That means if you want to add another part, you have to make sure that component's reliability value is higher than 95%. And as the number of parts increases, the reliabilities must be increased in order for the system to have a reasonable level of reliability. Reliability is used in the design of the system. And this is very important because part of the design is to make sure that you know how long your product will last, the life history curve. And this is the curve that we sometimes refer as the bathtub curve. And it is a comparison of failure rate with time. And it has the shape of a bathtub. In that specific figure, you will find 3 different phases. The infant mortality period, the bugging phase or breaking stage, which is in the one that you're going to find earlier failure, is because in this specific the failure rate is y-axis and then the hours are in the x-axis. Then the second state is the change failure phase, the operating stage, and this is what you're gonna have your product, your equipment at the useful life, and it's because most of the failures will be constant. And then you will have the wear out phase, which is where the failures rate will increase. So in the first phase is characterized by the marginal and the short life parts that cause a rapid decrease in failure rate. It might be part of the testing activity prior to shipment for some product. And here you're going to be using more the Weibull distribution, where beta is less than 1. Remember that they are different, and when we use reliability, we're going to be using a lot of continuous type of distributions. We're going to be using the normal, the chi-square, we're going to be using Weibull, we're going to be using the exponential. Those are the type of probability distribution that we use in reliability. In the second phase is when you see that failures will occur in a random manner, and this is due to the constant failure rate. And you can use either the exponential or the Weibull distribution, and the value will be equal to 1. Now in the third phase, the wear-off phase, you can either use the normal distribution or the Weibull distribution, where beta values is greater than 1. And at this phase, you're going to see that the failure rate will start increasing. You can use the exponential, and this could tell you a different stage, the binomial, the normal, the Weibull. If it's a breaking stage, it is recommended to use either the normal or the Weibull distribution. If you're having the constant failure, which is the second stage, you can use the exponential or the binomial. Or if data fit, you can use the normal or the Weibull. At the last stage, the wear-off stage, you can use the normal or the Weibull distribution. There are 3 basic measurements in reliability. The failure rate will tell you how many failures you have per an amount of time. The mean life is how long your product will last, how many hours in terms of time. And then you also have the probability of survival. If this probability of survival is high, well, it means that your product will last longer. If it's lower, your product will last less. So the failure rate, once again, refers to the failures per unit of time. And the symbol that we use is ln. For the mean life, is also known as the M or M bar, or the mean time between failures, or the mean time to failure. That is a system where no failures can be tolerated, and is reciprocal to the failure rate, lambda, and is measured in hours. Whatever value you have for lambda, the mean life, which is M or M bar, will be 1 divided by lambda. And then the last one is the probability of survival, which is known as PS or RRS or P. This is the formula. How do we calculate the failure rate, which is the number of failures in a test divided by the total time. Now, to calculate this total time, you're going to have different weights because it depends on the type of test that you are doing. If the test is time terminated, or if the test ends before all unit fails, or T for non-failed units is the test period. So you're going to have different ways to calculate that T, and we're going to see this in a second. The mean life is equal to 1 minus length. There are 4 different ways that you can calculate that T, and this is dependent on the different type of tests. The first one is the time terminated test, and this is where failures are immediately repaired and continued on test. It will be the sum of the T's. In this case, is the test period T times the sample size N. So it's N times T. This is the first way you do it. The second one is also a time terminated test, but here the failures are not repaired and replaced, but failure times of the failed units are logged. So the way that you calculate the total test here is the sum of the failure times for the failed units plus the remaining units, those that did not fail, times the test period. This is the way that you calculate that. The third type is the time terminated test, where the failures are not repaired and replaced, but the failure times are not logged either. So there are 2 ways to do this one. You either assume that all units has failed exactly halfway through the test, and this is a formula, or you assume that an average number of units completed the test, so you use this formula. But this is based on the design, based on the different criteria that you might have. And the fourth type of test is the failure terminated test, and this is where all units are tested to failure. The total test time is the summation of the failure times. So these are the different ways that you calculate that T that is needed to calculate the failure rate value. So in reliability, we have a way to calculate the reliability of the system. A system can be arranged in a series way or in a parallel way or a combination of both. You also can calculate the reliability value using failure rate. And the way that you use the failure rate is having the number of units that failed, and also be able to calculate the total time of failure, which is based on 4 different types of tests. This is the part of reliability, and once again, reliability is quality over time. Another part in the reliability field is what we call the maintainability. And we know that as the reliability of a system increases, the frequency of maintenance will decrease. And conversely, the frequency of the maintenance will increase as the system reliability is greater. So what it means that unreliable system will usually require an extensive maintenance. And there are 2 types of maintenance. There are the preventive maintenance and the corrective maintenance. Preventive maintenance refers to those that we have to do periodically and in which we have to repair or replace as the needs requires. When we have corrective maintenance, this refers to repairs only, and only when a component fails to operate, or when it causes the operation becomes really high, because it's at that wear out stage of the bathtub curve. Maintainability requires a confidence limit to provide a reasonable assurance of accuracy. Also, if you think about the normal distribution bell shape, maintainability is limited to a single side. Remember that we have alpha, and if we take into consideration both alpha and on each end of the tail, we're going to find alpha over 2 and alpha over 2. When we do maintainability, we use limited to a single side confidence limit, because we don't want to increase the maintainability. The faster the repair, the better. Also, there are factors that you need to take into consideration when you do maintainability, which is the maintenance labor hours factors, the maintenance cost factors, and this type of factors will be part of calculation of that maintainability. You also have availability. And availability, what it does is provides a prediction of the probability that a complex system will be ready for use at any moment in time. So it's available. There are three ways to calculate the availability. You have the inherent availability, and it's using the mean time between failures, and the M bar, which is part of the mean life. You also have the achieved availability, and it's using the mean time between failures as well, but it's using the mean life that is no CT. And then you have the operational availability, and it's using the mean time between failures and the mean downtime. So in terms of reliability, it's very important that you understand how maintainability plays a role and how availability is also part of this role. Also remember that maintainability is the easy with which preventive and corrective maintenance on a product or service can be achieved. And one of the best times to improve maintainability is in the design phase of a product or service. Also, improvements in design have resulted in, for example, in automobile, in 100,000 miles between automotive tune-ups, self-lubricating bearings, expert systems for service activities, and so forth. So this is how maintainability takes place in the reliability in design as well. Remember that maintainability uses a number of different figures of merit, such as the mean time to repair, the mean time to service, repair hours per, let's say, 100,000 number of operating hours, preventive maintenance costs, and downtime probability.